Okay, today's gonna feel different. Today is not what we've been doing thus far. It's gonna kind of set us up for dealing with area with a circle, but it's not dealing with area anymore, and it's dealing with circles instead of polygons, okay? So it does kind of move in a different direction. So if you are sick of polygons, this might be nice for you. If you really like the polygons, we gotta do something a little different for today. So here's the scoop. Circles and arcs are what we're talking about. And we're just gonna define a couple things, and then we're gonna define a lot of things really, and then do a little bit of work with them. So a circle, it's the set of all points, what, from the center? Anybody know?
Pi, 3.6.
There is 3.14. There is pi involved in these, but we're not there yet. It's the set of all points that are equidistant from the center of your circle, okay? And you name a circle by its center. So if you look at this circle right here, we would call it circle. And how you name it is you put a circle with a dot inside, okay? That's how you know it's a circle and not the letter O. So circle and then the center, circle X, okay? So you have segment AC there. If you look at this circle, notice it goes through the center. Anyone know what we call that segment?
Diameter.
It's the diameter, okay? AC is a diameter. So diameters go all the way across the circle. And then XB, this one here, goes from the center to the circle. What do we call that? A radius, okay? And often radii and diameters get confused. So here's how I tell people to remember it. The longer word is the longer line. The shorter word is the shorter line, okay? So the radius is shorter, right? Only has 6 letters. Diameter, 1, 2, 3, 4, 5, 6, 7, 8 letters is the longer word, if you need a good way to remember it. Then there's this angle AXB. So AXB is this angle. Okay, another way to name it would be angle X, but there's multiple angles coming off of there. So AXB using all 3 letters. We call that a central angle. And we've been talking about central angles for a little while. That shouldn't be a new term to you. But you're gonna hear a lot about central angles in this section, so keep it in mind. Okay, that is all the pieces of a circle. And now we're gonna talk about arcs in that circle, or in a circle. So the first, if you look here, notice my marking is not really an arc. An arc should be rounded. Those are pointy, but arc TRS, okay? Arc TRS means you start at T, you go through R, and you end at S. Anyone know what that arc is called?
Rotation.
When it's half of a circle? No. That's a semicircle. Okay. So arc TRS, when it's using a diameter, is a semicircle. Okay. Anyone know the measure of a semicircle? How many degrees? 180. It's 180. So the measure of arc TRS is going to be 180 degrees. It's half of a circle. A circle is always 360. Okay, so that's 180. Okay, arc RS starts at R and takes the shortest distance to S. So when they name it with 2 letters, always go the shortest distance. Okay, arc RS is called a minor arc. And a minor arc is always going to be less than 180. Notice they only use 2 letters when they name a minor arc. So just keep that in mind. When you see 2 letters, go the shortest distance between those 2 letters. That's your minor arc. Okay, then we have this guy, arc RTS. So RTS starts at R, goes through T and ends at S. Okay, notice it's 3 letters, right? That is called a major arc. And a major arc is always going to be bigger than 180. Okay. The way we often find a major arc is we take the measure of the whole circle, so 360, and we subtract the smaller arc, right? If I subtract this arc, the measure of arc RS from 360, I will get the measure of the rest of that arc, RTS. Okay, so example 1 here. We're just going to name some of these arcs, and we don't have to name every single one. We'll name a few. If you look at this picture, can anyone tell me a minor arc? AB. London, were you going to give me one? BE, okay. So AB would be a minor arc. BE is a minor arc. Notice they both only gave me 2 letters, right? That is a minor arc. Minor arcs will only ever be 2 letters. And it's always the shorter distance between them. So AB is here, BE is here. You could keep going, right? ED or DE is the same thing. And then AD or DA, same thing. Okay, those are all minor arcs. You don't have to write them all, but I will write them all here if you want to see them all. Okay, major arcs. And I feel like major arcs get a little more confusing because there's going to be some overlap now with which ones we've named and which ones we haven't. But if I need a major arc that contains point B, so let's just start at point B. Let's say I start here. Can you give me one major arc that starts at B? BEA would be one. Yep, BEA, that's this arc. From B through E, ends at A. What if I went the other direction from B? BAE or BDE would be the same one, right? So BAE or BDE, that would be this arc. Okay. What if I start at A, but I still want to use point B? What?
AE.
Not AE. So if I start at A, if I go AEB, we actually already named that one. Do you see where we named that one? We went BEA, right? So if you go the other direction, it's still the same arc.
Why do you keep skipping D? How do you get
You could use D, but you only need 3 letters. So if I said BDA or BEA, it's the exact same arc,
Oh.
right? A what?
AED.
AED, yes, yep. Technically, if we want to include point B, right, because it says containing point B, I would say ABD for that. But yes, it's the same arc, ABD, right? So there's a lot of major arcs that have point B in it. That's not even all of them, but I'm not going to keep going with that. Semicircles. How many letters do you need to name a semicircle? You need 3. Okay, but why do you need 3?
So it's not a minor arc.
So it's not a minor arc. Yeah, minor arcs are going to have 2. There's another reason. Like, why can I not right now say that my semicircle is BD?
That's just a diameter.
Okay, so you could think of it as a segment, but what if I wrote it like this?
You have to make sure which one's going.
It's not over, it's equal to 180, right? Right, and we don't know which side of the circle we're talking about. Is BD this one or is BD this one? We didn't specify, right? So when you name a semicircle, make sure you name 3 letters so we know which half of the circle you're referring to. So I would say BED. Okay, that would be the right side of that circle. What's the left side? BAD. Okay, do you see another semicircle? ABE would be one. And then what's the other side of it? ADE. Okay, and again, you could call it EDA, and it's the exact same arc as ADE. Okay, so don't worry about what order you're naming them in, other than you need your first and last to be where you start and where you end. Okay? Okay, so that's naming them. Take a look at this. In this circle P, right, you name it by its center, so this is circle P. If I know this angle, which we call a central angle, is 95 degrees, here's the beautiful thing about circles. The arc linked to that angle is the same measure. So if this angle is 95 degrees, then arc AB is also 95 degrees. Okay, so a central angle, maybe you want to write this down. Central angle equals its arc. Okay, a central angle equals its arc. Okay, so then there is what's called the Arc Edition Postulate, and I'm not even going to write this down because honestly, you guys, you've done it with angles, you've done it with segments. It's an addition postulate. All it says is if I take this arc AB, I'm going to write this. Arc AB, the measure of arc AB, plus the measure of arc BC, it will equal the measure of arc ABC, right? If I take the two arcs and I add them together, it equals the whole thing, okay? You've done it with segments, you've done it with angles, now we're doing it with arcs. I'm gonna show you how it works right here. Okay, so for example 2, I should have put more information on here for you, but I didn't because I was in a hurry. Here's what I want you to do. The black that I write in right now is given to you, okay? You don't have to find this. Do you need me to move?
Sorry, yeah.
So on example 2 here, we're gonna say they tell us this angle is 60 degrees and that angle is 20 degrees, okay? So that's given to you. Just write it in black so you don't think it wasn't there to begin with. Okay, we're gonna find 4 different arcs right now. First one that we're gonna find, letter A here, I wanna know what is the measure of arc TR. Okay, so remember TR, when we're using 2 letters, that's the minor arc. So we want the shortest distance between T and R. So from T to R, I want to know the measure of this arc. How many degrees is that arc? 60. A central angle will always equal its arc. Okay, and I think on these ones, you guys, if I were you, I would copy these in my homework, like from the book, and drop it into your homework, because it helps if you label things as you go, because you'll usually use parts that you found in other parts of the problem to finish off the problem. So I would label it as you go, okay? Arc TR is 60 degrees. Okay, letter B. What is the measure of arc TRS? So from T through R over to S. 180. It is a semicircle, right? That is half of a circle. So 180 degrees. Okay, so then what's the measure of arc UTR? It's 80. If you go from U through T over to R, okay, this central angle is 20, so the arc is 20. This is arc addition postulate. 60 plus 20 gives you 80 degrees for that arc. All right, last one. I want to know the measure of arc RS. 120. You found the whole semicircle, right? The whole thing was 180, and you take away that 60. That make sense? So a central angle always equals its arc. All right? Okay. We're going to talk circumference for a minute here. Anyone remember one or both of the formulas to find the circumference of a circle? Tessa. 2 pi r. Okay, so one of them is circumference equals 2 times pi times the radius. Or, what's the other one? If you double a radius, you get a what? Diameter. Okay, so the other one is pi times the diameter. So I don't care which formula you use. It's kind of a matter of how you prefer to think about it. But those are the formulas for finding circumference of a circle. Now here's the beautiful thing. Circles are always similar figures. Do you remember what similar figures are? Proportional, right? A circle is always similar to every other circle in the entire world because it's a radius related to a radius, right? There's not different dimensions that come into play. So circles are always similar, which means we have something called concentric circles. And concentric circles are just circles that have the same center. Do any of you watch Friends? Do you remember the scene where Rachel's making dessert, and Monica says, now you're going to want to put them in concentric circles. Do you remember that scene? It happens. I remember. No, she's putting, I think it's a Thanksgiving. She's putting marshmallows all the way around the topping. And she says, no, you want to put them in concentric circles. I want to do this. And she shoves a marshmallow up her nose. No? It's really fun. I love Friends. It's my childhood right there. Well, it's not my childhood. It's actually, Friends was on when I was your age. That's when Friends came out. Well, my parents didn't let me watch it at first because it wasn't the best. But then later in life, I watched it. And I love it. Anyway, so concentric circles are just circles that are going to have the same center. Okay, so there's your center right there. If you think back to chapter 9, we talked about dilations, right? So if I say this is my pre-image, and we're just going to call that length h, and then the bigger circle is my image, and we'll call that length k, okay? Remember we had a scale factor. So it's your image over your pre-image. Your scale factor would be k over h, your image over your pre-image. You won't do a ton with that, but I just want you to kind of be seeing it as that dilation setup that we did with chapter 9. Okay. We're going to try a problem that kind of uses this circumference idea. Any of you watch NASCAR? NASCAR always turns what direction?
Clockwise.
Always go left. They always go left. So let's say you have a car and you are going to be driving that car in a circle. I know NASCAR is not a circle, but use your imagination. Which set of tires will wear out faster?
The front, back,
Which one?
inside. The left side.
Which one's going to drive further in one circle?
Left side.
The outside, right? If I drive in a circle, my outside tires have to travel farther, right? So the outside would be wearing out sooner. So here's the question. How much farther would those tires travel on the outside loop than on the inside loop? Okay. What are we finding? If we're finding the distance a set of tires travels, what is this in a circle? Circumference, perimeter, right? So if we want to find the circumference, what's the circumference of, let's start bigger. What's the circumference of the bigger circle?
360.
2 times pi of the bigger circle, though. Sorry, I switched it up on you. Of this circle. 2 2 times pi times the radius, right? Or pi times the diameter. The diameter of that circle would be 20. So the circumference of the bigger circle is 20 pi feet. Okay? What's the circumference of the smaller circle? Two times pi times 7, the radius of the smaller circle. Okay, or if you're thinking of it pi times diameter, the diameter would be 14, right? So it's 14 pi feet. Here's the question. How much farther do you travel on one loop of the bigger circle? What do you do?
20 minus 14.
20 pi
Oh, yeah.
minus 14 pi, which is 6 pi. 6 pi feet is a weird answer. Like if someone says, how much farther did you go? You're probably not going to say, I went 6 pi feet farther, right? So just plug that in. What is pi as a number? 3.14. Or there's a pi button on your calculator. Just use the pi button. 6 times pi, if we round that, it's about 18.8 feet farther. Okay. Questions on that? So that's circumference. How much farther did you go? The distance. Yeah.
Why does everybody love pi? Like, why does that number get its own little variable?
Because that's like, it's not a variable. It's a number.
It's like the little pi. Like
It's a symbol, right? But that symbol represents a number. And you can't just say the number is 3.14 because pi isn't 3.14. Pi is a number that never ends, right? So we don't want to call it 3.14. If we want an exact answer, it's pi. You got to use the symbol.
Why would someone make that? Like, it never ends.
Someone didn't. God made it. Like, it is something they discovered in mathematics. Isn't it beautiful? Like, what a beautifully ordered, glorious world that he made. No, I mean, there's an infinite number of numbers, so there is no end. Yeah, it is crazy. Okay, anyway, here is some terminology that I need you to be very clear on. So if you checked out, check back in, hear me on this, okay? At times I'm going to say arc measure, and at times I'm going to say arc length. They are not the same thing, not even a little bit, okay? Arc measure, when we talk about arc measure, we're talking about how many degrees an arc is. When we're talking about arc length, we're talking about how many centimeters or feet or inches an arc is. Okay, they're very different. So just make sure you know the difference between those. For instance, let's say I told you that this is a 60-degree central angle. Okay, that angle is 60 degrees. If I was talking about arc measure, I'm going to color code here, okay? Arc measure, what is the measure of this arc, the closer one? How many degrees? 60, okay? 60 degrees. How many degrees is this arc? 60 degrees, okay? So your arc measure here is the same. They're both 60 degrees. They're both 1/6 of a circle, okay? Arc length, if I'm talking about the length of this arc versus the length of that arc, are those the same? No, that outside line is longer, okay? So arc length and arc measure are very different. Make sure you pay attention to length versus measure. Measure is always degrees. Length is always units, inches, centimeters, whatever it is we're talking about, okay? Okay, so with that in mind, I have a formula for you to find arc length, okay? This is on that formula sheet that I put in Canvas for you. So if you're doing the homework and you want to just pull up that formula sheet, it's not a terrible idea. I highly recommend it. Yes,
Will
sir.
you ever get the same arc length?
Arc length and arc measure? Or just, yes, I mean, you can totally get the same arc length, right? Think of it this way. Okay, if I took this and I said this length right now is 2 centimeters, okay? I can have a 2 centimeter arc on a bigger circle, right? This is the same length, but now its measure is not the same. That angle's smaller than that one, so the measure is different even though the length is the same. Yeah, so you can have it either way. Okay, but the formula for arc length is this. It will say the length of an arc is the measure of that same arc, okay, so how many degrees the arc is, over 360 times pi d. Looks like a really confusing formula, but when you stop and think of it, it is not. This right here, that's a fraction of a circle, right? Some fraction of the circumference of a circle is your arc length. So it's very like just plug numbers into a formula and it will do the work for you, okay? You're taking a fraction of the length around a circle. Let me show you what I mean. Look at example 4. It says find the length of the arc, okay? They're talking arc RS, so RS is right here. Okay, now when it says the measure of arc AB, AB is a generic arc. It's just saying what's the measure of the arc we're talking about. So what is the measure of arc RS? 90. Yeah, the measure is 90. So you're going to say 90 over 360 times, now go back up to the formula, what's the circumference of that circle? 12 pi, right? Pi times the diameter, or pi times 12. You're almost done. Here's all you do. You plug everything into your calculator except for the pi. So plug in 90 divided by 360 times 12, and you should get 3. Then you can drop the pi in, and it's a length, so it is 3 pi centimeters long. That makes sense? Yeah.
We're not going to do any of that squaring stuff right this time.
You don't square it because it's a length. If it was an area, then you would square it. You'll get an area formula the next day, tomorrow. Okay, this one. It says, find the length of arc RTS. So RTS, notice, R through T to S is this arc. We need the measure of that arc. What is the measure of that arc?
360 minus 100.
Yeah, 360 minus 100 is 260, okay? So 260 is the measure of that arc. So we're going to go 260 over what? 360 times pi times, not 9, 18, the diameter, right? Times the diameter would be 18. So you have this, you're going to plug this into your calculator. 260 divided by 360 times 18, and you get 13. Then drop the pi in. And then whatever your units are, this is feet, so 13 pi